Hi there.
Okay. Oh my gosh. All right. So, our story yesterday was a story of uniform circular motion. And what made the motion circular is that the object is moving in a circle. But specifically, that means that the object's distance from the center is constant. What do we call that distance from the center?
Radius.
Radius. And what made the motion uniform is that the object's speed, we're going to spell as the magnitude of the velocity vector, is constant. And so our typical scenario is a golf cart toodles along at 2 miles per hour around a circular track of radius 400 meters or something. Toodles. Yes. All right. And so what we discovered yesterday when we did the exploration is that these two facts force several things to be true. First of all, what is generally true, whether circular or not, whether uniform or not, is that the velocity vector is always tangent to the path. So that if I am drawing the motion of this object and it is going around the circle, I can immediately draw the velocity vector as tangent to the circle, just like so, whether clockwise or counterclockwise.
I draw this on tangent part.
Why should it be tangent? Okay. Can I explain this without calculus? No, you asked for it. All right. So
Here we go.
yeah, here we go. So one way to answer that question is that if I am trying to find the velocity vector, then this guy right here will be an average velocity vector that connects from one point to the next. Okay? And if the average then is going to be delta x over delta t, or delta s over delta t, if we take it as a position. If I now take the limit as delta t goes to 0 to get an instantaneous velocity, then what I'm talking about is taking this second point x, final, and we're essentially going to move it along the curve right here until we get to right here, because we are taking smaller and smaller time intervals, and therefore we go a smaller and smaller displacement for each time. And finally, as our time interval vanishes, so does our displacement, and I'm left with a slope just at the single point, so that the velocity is now tangent to the curve. You asked for it. In more calculus 2 terms, we would say that the velocity vector is dx dt comma dy dt, and it can be shown that dx, the slope of that velocity vector dy dt over dx dt is just dy over dx, which is an application of chain rule.
And tangent is the adjacent over.
Oh no, he's thinking of like trig function.
Oh,
Yeah,
yes, okay. So here's an interesting and weird thing. The word tangent
It's not.
means two different things that are interrelated.
Math is evil.
No. Math is history, and that history is actually connected. So
Which is also evil.
the word tangent means something that touches the curve at a single point.
That's all it means.
Okay, that's all it means in this context. But in trig, you have this function called tangent that is actually the length that you get if you take a unit circle and make yourself an angle right there and draw the tangent segment right here to where that intersects the angle. This length will be tangent of theta. So the tangent of theta is literally the length of a tangent segment. So, and it all goes back to a single word, the Latin tangere, which means to touch. Tangere to touch. Yep. Math is full of Latin-derived words, and tangent is one of those. We even have, this was kind of fun, something I did in one of my grad school courses. We had curves that would come along and touch and go in the same direction as, and we called them osculating curves. Osculare is the Latin word for to kiss. So these are the kissing curves.
I just think that.
Yeah, go ahead. You would get the length of that tangent segment. Yeah. Yes, because it's in a unit circle, and in a unit circle, in a unit circle, your radius is 1. So this length divided by that length is tangent theta over 1. So opposite over hypotenuse is also true. And it's essentially taking our unit circle and expanding it to a circle of larger radius so that you have similar triangles. So opposite over hypotenuse is really a similar triangle thing. Now, opposite over adjacent, excuse me. I said the wrong thing. Okay? Okay. Side trip over. So, first thing we saw yesterday is the velocity is tangent to the path. The second thing that we saw is that in order to make the object change direction, the acceleration has to be pointed perpendicular to the velocity directly in. What are you listening to? Just tell the truth.
Like my mom sent you a message, like voice message.
Okay. Just wait. Not directed at Elliot in general, but really directed at our election in particular. Our country has a challenge with truth-telling. And we want to fight back against that. So tell the truth. All right. Velocity is tangent. Acceleration is, and here is our Latin word from yesterday, it is centripetal. It is center-seeking. It will point inwards towards the center of the circle. So that if my velocity is like so, my acceleration will be like so. And it must be pointing straight inwards because if it pointed forwards, the object would speed up. And if it pointed backwards at all, the object would slow down. And then finally, what we found out yesterday at the end of class, and I'll walk through the derivation one more time, is that the magnitude of the acceleration that is needed in order to make the object move in a constant circle with uniform circular motion is v squared over r. And the reason for that is as follows. If I take an object that is moving along a circle, like so, and I consider its velocity vector that is tangent to the circle, and then I let it move for a little bit of a distance here, r1, with a new velocity vector v1 that is tangent to the circle again. What has changed from v0 to v1 is not the length of that vector because the speed is constant. What has changed is just the direction. And so I can now form two triangles, one of those between v0 and v1, and both of them are isosceles triangles because they both have, both of them are isosceles triangles because they both have two congruent sides. How do I know that they're congruent? Well, R0 is congruent to R1 because I'm moving in a circle. And V0 is congruent to V1 because I'm moving with constant speed. Everybody see how that works out? And I argued yesterday that these two central angles have to be the same. And they have to be the same because V0 is perpendicular to R0 because tangents to circles are perpendicular to radii. The only question then is, what can I do with this fact? Well, I notice that this little segment from v0 to v1, this little vector from v0 to v1, is the change in the velocity that occurs over that time. And this little segment from r0 to r1 is the change in the radius vector over time. Notice that both of these are really purely direction changes, because the radius is not changing in length, and neither is the velocity. And now we have similar triangles. All three angles are the same, and so we can set up a proportion. Specifically, we can set up the proportion delta v is to v0, just like delta r is to r0. Not quite done yet, but let's pause and see if there are any questions that this raises in your mind.
Wasn't it just over time? Change time?
Yeah, we're about to get there. Yeah. So far, I haven't talked about how long it takes for this process to happen. I've only observed the geometry of the situation. We're about to introduce time here in just a second.
No.
Good. No questions? Is everybody comfortable with the similar triangles? Yes, sir. That's an interesting question. No, actually, because delta r is not tangent to the circle. Delta r actually cuts across the circle, like that. It's connecting from one point to the other. So delta r will not be related to tan theta. And delta v also not related to tan theta. Delta v actually points inwards towards the center of the circle, more or less, because it's the change of my velocity vector as I go from v0 to v1. And you can see it points in like that. Okay, now let's introduce time and see what we see. I'm going to divide both sides by delta t. And I'm going to write my division here as multiplying by the reciprocal. And I'm going to do that on both sides. So in some sense, this is a purely algebraic thing. What I'm really doing now is computing rates. Before, I looked at this only from a geometrical standpoint. Now I'm actually going to let the clock run and see how long this process takes.
What do these do?
I just divided both sides by delta t. But I also wrote division as multiplying by the reciprocal on both sides. Question? Now, delta v over delta t, we know that's acceleration. And specifically, we know that it's centripetal because it has to be pointing straight in. And 1 over v0 is the length of v0, that's just the speed. We're going to call that v. Delta r over delta t is the average velocity over that time. And the length of the average velocity is going to be the same as the speed also, because the velocity is not changing in its length as it goes. And finally, r0 is the length of this vector right here, which is the radius of the circle. Well, now it's just a matter of multiplying both sides by v, and I have it. In AP Physics, we get this exact same equation, but we do it from a completely different standpoint, from the standpoint of calculus. Yep.
Where'd you put the V? Just above here, the formula.
Here?
Other.
Here. Ah, yes, so delta r over delta t is a change in position over a change in time. It's an average velocity. And its length is going to be the speed of the object.
Okay.
Yeah. Sure can. And as I said yesterday, the takeaway from all of this is that when an object is moving with uniform circular motion, it will always have a centripetal acceleration. Centripetal means what? Center seeking, right? Centripetal, center seeking. And the value of that centripetal acceleration will be v squared over 1. So this is going to extend our use of Newton's laws. And when we did Newton's laws in the previous chapter, we used our equations of motion for constant acceleration because we were working with situations that involve constant acceleration. Now we're going to also consider situations of uniform circular motion so that our acceleration will have a different value than it did for previous problems. Yes, sir? Mm-hmm.
How do you get the V?
Which one? Here or here?
The second one.
The second. This guy is the change in the position over the change in time. And change in position over change in time is average velocity.
Can you just compare 0 where for the 1 where velocity and 1 where...
Yes, because both V0 and V1 both have the same length because I'm moving with uniform circular motion. Yes,
There's such thing as non-uniform circular motion?
there is.
So that's the velocity.
That's where the
If
velocity.
increases, wouldn't it not be a circle anymore? Or is it more
It'd be like an oval.
It could be, so that would be non-circular motion, or you could have a car drives around a circular track and it speeds up, starts at 0 and goes to 60.
So
So you can have both. You can have non-uniform circular motion.
with the centrifugal force increase then?
Yeah.
Okay.
Yeah. Now don't confuse the word centripetal, center seeking, with centrifugal, center fleeing.
But they're both related to circles.
They're both related to circles.
I know I've heard centrifugal.
You've probably heard centrifugal force a lot, yeah.
Yeah.
And we'll talk about that at a future time. Objects moving in circles do not experience a centrifugal force.
Yeah.
Or at least if they do, it's a clever fiction. But more on that in the future. Okay, how are we doing? That's our review. Now, homework questions. Somebody said number 3.
Oh, this is not...
Calculate. The centripetal acceleration of the Earth in its orbit around the Sun and the net force exerted on the Earth.
You needed like so much outside information for this problem.
Yeah. That's a good point. For these astronomy problems, very often we end up having to look up
Yeah.
constant values. Yeah. And then they want to know, what is the net force? Okay. Guess what I'm going to start with? Done, right? In my free body diagram, I'm going to show that the Earth is moving in a circle around the Sun by drawing some sort of arc of the circle. And now, what force is acting on the Earth? That's it. It's gravity from the Sun. Here comes FG. But it's probably not going to have a value of m times g. In fact, it doesn't. Because we're talking about one planet attracting another planet here. Yeah. Okay, so that's my force. And notice how I knew which direction to make it point. Which way did it point?
Or the central.
What's our word?
Centripetal.
Centripetally, that's right. It's a centripetal force. Okay. And so now I can say that the acceleration is simply v squared over r. And that's done. I get to plug in. Ta-da! Oh, wait a second. I need some values. I need the radius of that orbit. Aha! Assume that the Earth's orbit is a circle of radius 1.5 times 10 to the 11th meters. Okay, that's good. What about the speed of the Earth? No idea.
What
Okay.
about Google?
You Googled it?
Yeah,
What'd you find?
30,000 meters per second.
Dang.
Right.
Did you know that we're going 30,000 meters per second around the sun?
Wow.
Wow! Yes! Wow, indeed. How come we can't feel it?
Because we can't feel speed.
Because you don't feel speed.
Like,
Wow.
how fast is that comparatively?
30,000 meters
If
per
there-
second
if there
is 66,000 miles per hour.
My
So, like,
gosh, that's so
We
weird.
don't even have anything that would compare to that kind of speed.
We have nothing on Earth that can compare to that speed,
Yeah.
really.
Wow.
Well, actually,
Except for Earth.
like
Yeah.
ballistic missiles, I think, can approach. I think they get to speeds of like 10,000 meters per second. I think that's right. That they get to speeds of
That's only a
10,000
third
meters
of
per
it,
second. That's only a third. That's right. Yeah.
Multiply
Now
by
you
three.
can understand why even a relatively sort of medium-sized asteroid would cause humongous damage if it hit the Earth.
It's asteroid.
Space rock. Okay. So how are we going to get that speed? We can look it up, and if we look it up, we get our answer, and here it is. If we did not know it, we could actually generate it. And we generate it from the fact that we are moving in a circle. So I want to take a minute to make sure that we can all do what I call circle calculations. There are three interrelated quantities for a circle. The radius, the rate at which the object moves around that circle, which we can measure in terms of the period of revolution, and this is the amount of time to complete one circle, to complete one revolution. And we're going to give the period a symbol capital T for time. And then finally, the speed. And these are related in this way. If I go all the way around the circle once, then I have gone for a time period of t. And I have gone for a distance. Notice I did not say displacement because my displacement is 0 when I go around the circle once. I've gone for a distance of the circumference of the circle, which is 2 pi r. So that one circumference is the same as one period. One circumference in distance is the same as one period in time. And therefore, the speed is distance over time, as it always is. That would be average speed, but because I'm moving in uniform circular motion, that is also my speed at all times. Which would be 2 pi times the radius divided by the time. Well, we actually know these quantities for the Earth because in the problem they give us the radius of our revolution, which is 1.5 times 10 to the 11th. Meters. And we also know the period of revolution of the Earth. What quaint English word do we use to describe the period of the revolution of the Earth? A year. Yep. 1 year. which is 365 days. Where does that 0.25 show up in these?
Leap year.
Leap year, that's right. And is it exactly 0.25? No, it's like 0.24 something. So there are special rules for leap years. And do you know when leap years happen? They happen every 4 years, except they don't happen every 100 year, except that they do happen every 400 year. And that basically kind of keeps everything on, that keeps our calendar synchronized. But even there's a little bit of round off. So last year we actually had a leap second. Just boom, at midnight, there was 1 extra second.
But all
Wait.
of
Why?
But since all time is relative to begin with,
Why do
Why
they do
can't-
that?
because
They
we don't
do
stay
that
on the
because
same-
otherwise what we're really trying to do is to synchronize our clocks with our
Yeah.
calendars. The
okay.
clocks and the calendars are doing different things.
Alright.
The calendars are based upon day and night,
Yeah.
and the clocks are based upon 24 hours.
Yeah.
Right.
Just 1 second.
Why don't they say, like, tell people there's a second? They did.
Oh.
It was announced. Where? In the news?
I've never heard of it.
Yeah.
We're probably all doing.
You can do
We
it.
were doing physics.
Okay, now we need to do some conversions here because days is a very, very unfortunate thing. And at this time, I'd like for all of you to convert 365.25 days into seconds because we're going to find something nifty.
31,536,000.
That's
going off 365. Then. We didn't. Yeah.
Go ahead and do it more precisely because I want to make a point. Uh-huh.
So he originally rounded off this at 1.4, and it made it like 4,000. Because this reflects so much value.
This is like,
Uh-huh.
milk.
3.16 times 10 to the 7 seconds. Okay? Now here's the point that I want to make as an easy way to remember it. Although it's not fully accurate, this is how I remember how many seconds are in a year. Pi times 10 to the 7. It's not perfect, but it's pretty good approximation. Why? It's just a coincidence. It just is a coincidence for the Earth. For Mars, if we lived on Mars, it would be a different number, much larger. As you move out, we'll discover this later, but as you move out, you can imagine that your year takes longer.
So there's like,
Yeah, slightly small. It's off by 2 parts out of 300. Okay, so that finally gives us our speed, and when we compute that speed, what we get when we compute that speed, what do we get? It's kind of nice because the pi's cancel out in our factor there. Three. Yeah, I get just about 3 times 10 to the 4th meters per second. Or 30,000 meters per second, exactly as Alexis/Google predicted. Hey, yeah, totally cool. Yep. All right. So we've got our speed, and now it's just a matter of plugging it in. 3 times 10 to the 4th meters per second. And when we plug this in, let's see if we can do this in our heads. 3 times 3 is going to be 9 divided by 1.5. 6, that's right. 10 to the 4th squared is 10 to the 8 divided by 10 to the 11th. 10 to the negative 3rd, that's right. What about my units? These units are interesting. Meters squared per second squared divided by meters.
You're gonna get us acceleration.
That's right. You get a meter left and a per second squared. What do you think about that acceleration?
That's pretty small.
That is pretty small, 0.006 meters per second squared. How does that compare to g?
Well, I mean, it's-
You don't feel it.
but it makes
Bingo.
sense.
That's right. Why does it need such little acceleration? Well, it's not because of our speed, because our speed is faster than anything we're used to land-based. But look at the size of that radius. That radius is so large, that it doesn't take much force at all to push the Earth in a little gentle circle. Large circles require small acceleration. Tight circles require a large acceleration, because you have to change your velocity quickly as you go around.
Okay.
So because
Because it does click with me that this acceleration is pushing it this way, so it's a curve.
Yes, that's
It's like
it.
the illustration you showed in class.
Yes.
Just click.
Yeah, good. Good. That's really my job, is to create pictures in your head.
it doesn't like a meteorite that hits the Earth and throw it completely off. It's like that.
Good question. So if a meteorite hit the Earth, would it throw it completely off? Here's the interesting thing. If a meteorite hits the Earth, and actually we get collisions with little bits of space junk, you know, all the time, then we have two things to consider that we will discuss in a future time: energy and momentum. The energy of that meteorite is pretty large because of the high speeds. But the momentum of the meteorite compared to the momentum of the Earth is pretty small because of the low mass. Okay, does this make sense to everybody? Good. Now what about the force? Here's the interesting thing. For all that patheticness of our acceleration, the force is still pretty large, because of course we all know that F net is equal to ma. And we look up the mass of the Earth. Alexis probably did that. What'd you get?
It was in the book, 5.98 times 10 to the 24th kilograms.
Yeah, that's a lot. So that when I multiply my puny acceleration times my humongorific mass, what I get is going to be basically 6 times 6, or 36, times 10 to the 21st kilogram meters per second squared, or newtons. That is a huge force.
That's the forces causing the Earth.
And that's the force that's causing the Earth to curve. And it is the gravitational force that is exerted by the sun. Later, we will discover that that gravitational force is really caused by the combination of the sun's mass and our mass.
So that's like the centripetal force.
It is a centripetal force. That's right. The centripetal describes its direction, pointing in towards the center. Its nature is a gravitational force. Yes? 10 to the 21st. This is fake scientific notation. I do this a lot. 6 times 6 is 36. If I want to write it in scientific notation, I need to roll up my decimal properly, so that it's 3.6 times 10 to the 22nd. Does that make sense?
Oh, okay. It's about it.
Yeah.
Post this on Google. Sure.
Be happy. Okay, I want to extend this a little bit, and
36 times 10 to the
I want to take a look at problem number 10. Sure. this is kind of a classic here. What we have is a car going around a curve, and when that car goes around a curve, it is going to need a force that is going to keep it on the curve, to keep it from sliding off and going straight, drifting, right? What is that force that is going to keep the car from doing that?
Friction.
It's got to be a frictional force. The nature of the force will be frictional. We never want to call a force centripetal when we're trying to describe what it is. We use the word centripetal to describe its direction. So we're going to have a frictional force here, in other words, the tires gripping the road, that is pointed centripetally so that the car does not slide off the road. Here's what this looks like. Here comes my road, here comes my car. If the tires adequately grip the road, then it's going to supply a force of, they will supply a force of friction that is pointed inwards towards the center of the circle, causing the car to turn. If the tires fail to grip, for whatever reason, the car will slide off and move with constant velocity.
So the friction's pointing in because it just wants to go.
Because the car is basically trying to go in a straight line, and the friction is saying, no, you have to go along the curve.
Doesn't friction oppose motion? So in that like.
But in this particular case, the motion that it is opposing is a motion of going in a straight line. Yeah. So here the friction is going to change the direction rather than the speed. Prior to this, all of our frictions have slowed our objects down, basically. Now we are having friction that is going to change the direction of motion.
This is what happens when you turn the wheel.
Yes. When you turn the wheel, what literally happens is the tires turn. Because they are turning, now there's going to be a frictional force that is pushing essentially from the road. Now, the first thing we notice is that our speed is unfortunately given to us in kilometers per hour. Then go ahead and convert. Quickly, don't have a lot of time. 0.02 meters per second, really?
That's 1.4.
What'd you get?
6.4 meters.
Ah. Yeah. Or about 55, 60 miles an hour, something like that. Okay. So this is our setup. This is a top view. To do this adequately, I think it's best to take the car in a side view. Particularly, I'm going to take the car from behind. So if this is my car now, with the wheels sticking down like this, the wheels are going to experience a frictional force like so. The car is going to have a normal force with the road, and of course it has a weight pulling it straight down. The reason I don't want to do the top view for this is that, as you know, the weight and the normal force will be pointing into and out of the board, and that's hard to see. So if we now do the sum of forces in the y direction here, then we get, surprise, surprise, Fn minus mg is equal to 0, where the normal force is equal to mg. We've seen a whole lot of that. If we do the sum of forces in the centripetal direction, notice how I'm labeling that as Fc rather than Fx, because as the car goes around like so, then my direction is going to be continually changing. But what is always true is that the friction will be pointed in towards the center. So I'm going to let my axes float, so to speak, so that my direction towards the center is always the direction towards the center. That's a centripetal point of view. Does that make sense? So I do my sum of forces centripetally, and that sum of forces is simply friction. And because it is centripetal, that means the acceleration is automatically v squared over r. That's the key to this problem. So that my sum of forces is mass times AC, or mass times v squared over r. Is everybody with me? This was the key move here.
You're allowed to leave. Your x-axis forward.
All I'm doing is I'm making my reference frame the car.
Yeah. Yeah, just in how you can do that. The friction and acceleration are opposite directions, so
The friction is pointing in, it's causing the acceleration.
okay. So the friction and the acceleration, since they're both pointing center, they're going in the same direction. Are they on the same vector?
They are parallel vectors. They measure slightly different things. The acceleration is measured in meters per second squared.
Okay.
The friction is measured in newtons.
Yeah.
The friction will be mass times that acceleration.
Okay.
So that's
And then is the mass separate from the fraction, or is the mass on the
doesn't matter.
doesn't matter? Okay.
In
Yeah,
v
I
squared
got it.
is immovable into v squared.
Yeah. So it's essentially mv squared.
Yes.
The acceleration is going to be, square.
The acceleration is v squared over r. Yes, exactly. Well, now we're ready to use our friction relation. And because it is static, why is it static? Because the cars are gripping the road and not sliding. Therefore, I can say that the frictional force must be less than or equal to mu times the normal. And I have an expression for the normal force, and I have an expression for the frictional force. So that the minimum value of mu that I can have will be v squared over rg. And we have all of these values. We have 26.3 meters per second for the v. And we have 85 meters for the radius. And of course, g is 10. So that when we plug in all these values and divide, what we get is 0.81. Now, if you're going to do this, you don't want tires that have a mu of 0.81. You want tires that have a mu of 0.9 or 1.0 or better. Because this represents the breakthrough point. This is the point at which we're just about to start to slide. So that if your road conditions are not perfectly dry, or there's a little bit of oil on the road, or a little bit of water on the road, or even leaves on the road, then you're going to slide off. So this represents right here the worst case scenario. And engineers always take the worst case scenario and then they try to sit very comfortably inside it. So when tires are manufactured these days, tires typically will have a mu of 1 or larger. And those typical mu values are the factor that goes into computing the maximum safe speed around the curve. So when you see a curve sign, the yellow signs that say 20 miles per hour or something like that, what they're basically doing is they're taking typical mu values, taking typical speed, or taking the speed that they want and the known radius of that curve, and they're literally using this equation right here. So you are all now qualified to become civil engineers. Well,
Yeah.
So we should take
That's
the
crazy.
sign now.
Good job,
We
man.
should take the sign.
you should take the sign seriously.
Okay, all right.
Yeah. They cheat a little bit. They don't give you the absolute maximum speed, but under rainy conditions, yeah. Like Mr. Gaggle.